Okay, so before we talk about using geophysical techniques to figure out the inside of the Earth, what did we know about the inside of the Earth at the early 20th century? So let's say that you lived in the 1930s, the 1940s. What would you have known about the inside of the Earth? Okay, first of all, you would have known that the Earth formed as a result of collisions of asteroids. So, therefore, the overall composition of the Earth, so the elements that are inside the Earth, should be the same as the elements found inside of an asteroid. And so, since we have meteorites and we can analyze those chemically, we have a good idea for what are the basic elements inside the Earth. Okay, then the next thing is the density. So density is mass divided by volume. So it's how compact an object is. So we measured the density of asteroids, and we found that they were about 5,500 kilograms per cubic meter. Okay, the next piece of evidence or knowledge that we knew was the radius of the Earth. And so this was the earliest measurement of the radius of the Earth was done by the ancient Greeks. And so what they noticed was that on a certain day of the year, sunlight would go straight down a well and you could see the bottom of the well. But yet, if you moved away from the that well, 50 kilometers or so, sunlight, that same sunlight at the same time would not go down the well. So you would not be able to see the bottom of the well. Well, what that means is that the Earth is curved. So if the Earth was flat, then that would mean that on that same day, light would go down basically all wells and you'd be able to see the bottom of them. But on the other hand, if you take that flat surface and you curve it, well, now you can see why light would not go down a well that is a distance away from the one where the light did go down. So they used proportions to figure out the radius of the Earth, and they got a number that is within 1% of the accepted number for the radius of the Earth, which is about 6,380 kilometers. Okay, the next thing is, how do we figure out the mass of the Earth? So if density is equal to mass divided by volume, then if we rearrange that, we get mass is equal to density times volume. So all you got to know is what's the density of the Earth, and we got that from knowing what the density of an asteroid was. And then if we know the volume of the Earth, and so we get that by knowing the radius of the Earth, then we can calculate what the overall mass of the Earth is going to be. Okay, now the next step is quite a bit harder, and that is to figure out what's the temperature inside the Earth. So, in order to do this, first you have to remember, how did the Earth form? So the Earth forms as a result of collisions by tens of thousands of asteroids. So if you can imagine taking a globe, your typical globe, drilling a hole in the top of it, and then putting a BB into it, how many BBs do you think it would take to make up that globe? 10,000? Okay. So imagine how many asteroid collisions it took to build up the Earth to what it is today. Now, each of those asteroid impacts caused the Earth to heat up a little bit, because we had a formula for kinetic energy, and that was equal to 1/2 mv squared, where m would be the mass of an object, v would be the speed of an object, and then this would be the energy of the object. So each of those asteroids had a mass. Each of them were traveling with a certain speed, so when they collided with the Earth, they gave the Earth a certain amount of energy. And so that energy was turned into heat, and so we can measure that heat in terms of the temperature. So that's hard to do, but we can estimate what was the original temperature of the Earth based on the amount of collisions. Okay, then the Earth is also being heated up by radioactivity. So there are things like uranium and thorium, and as they break apart, they give off energy, and that energy is also increasing the temperature inside the Earth. Okay, then you also have to take into account, do you remember we said that the iron collapsed to the core? Well, just like if I take this thing and drop it, do you hear that energy being given off? So as that energy was, or as that iron was falling to the core, it was giving off potential energy, which was again being turned into heat, and then we measure that heat in terms of the temperature of the Earth. Well, then we have to take into account how much heat is being lost by the Earth. So ever since the Earth formed, it's been cooling off. So the heat has been coming up to the surface and then has been escaping into outer space. So this is pretty difficult, but based on these ideas, we have an idea for how does the temperature vary as you start at the surface and then as you move to the core. Okay, then the next thing is, what about the pressure inside the Earth? So pressure is going to be the amount of force being applied to an area. Now the amount of force is going to be the weight of the material that's on top of you. So if you go into a swimming pool, you feel the weight of all of that water on top of you pressing against the area of your body, and then that's the pressure being exerted on your body. So in this case, we need to figure out as you start at the surface and make your way to the core, how could we calculate the amount of weight of all of those rocks on top of you and then calculate the pressure down to the core? And so that has been done, and so here is a little formula for it. And so you see it's 2/3 pi. Now g is a constant that goes with the force of gravity. So you can see that this formula involves gravity, because gravity is what's pushing down the weight on top of you. And then it depends on the density of the inside of the Earth squared, and then it also depends on how deep you are inside the Earth squared. So I'm not going to bother to derive it. You have to use calculus in order to derive that equation, but at least it gives us an idea for approximately what the pressure is inside the Earth. I say approximately because this is assuming that the density is the same as you go deeper inside the Earth, and it's not, because the deeper you go, the more everything gets squeezed together, and so the density also changes as you go inside the Earth. But this is a good first approximation for the pressure inside the Earth. Okay, then the next thing is, how do we know the rocks that are inside the Earth? Now we have to go to chemistry. And in chemistry, chemical reactions are going to be controlled by temperature, pressure, and then the available chemicals that you have to work with. Okay, so we now know what the temperature is, or at least we think we know what the temperature is as we go deeper inside the Earth. We now know how the pressure changes as we go deep inside the Earth. And then we also know what is the Earth made of, because it was based on asteroids. And so you put that all together, and so chemists can predict what kinds of substances and whether they be solid or liquid as you go deeper inside the Earth. Okay, and then they also would know that the iron went to the center of the Earth, so they knew that the Earth had this big iron core, and they also knew that iron produced magnetism. All right, so that's pretty much the state of affairs that we knew back then. And so here's a picture of it. So that the Earth would have consisted of a iron nickel core surrounded by dense rocks called the mantle, surrounded by not so dense rocks, which we call the crust. Okay, in our next segment, we are now going to use ideas from seismology in order to figure out the different layers inside the Earth.